So this is my module one, theoretical yield and percent yield, fall culminating project. It's presented by Joshua Shung. So first to do some review of theoretical and actual yield. So theoretical yield is the maximum amount of product that could possibly be formed from the given amount of reactant, and it is calculated by balanced equations. And the actual yield is the amount of product that is actually obtained from the reaction, and it is usually a smaller quantity compared to the theoretical yield due to loss in product or interfering reactions. So to do a quick review of percent yield and the limiting reagent, we have percent yield, which is the ratio of the actual yield to the theoretical yield as a percentage. And then below that, we have the formula to get percent yield, which is actual yield divided by theoretical yield times 100. And that would give you your percent yield. And then for the limiting reagent, it is the reactant that is completely consumed in a chemical reaction. And then in the diagram, as you can see, I provided below, uh, there is an example using hot dogs and buns as the reactants, and you can see that the buns are the limiting reagent because it results in having fewer in the theoretical yield, and then leaving the hot dogs as the excess reagent. So in this slide, we're going to talk about what percent yield determines, and you can see here when it's less than 100%, from 50% to 99%, it is normally caused by inefficient reactions that don't go till completion, side reactions, and products that are very difficult to recover, and it's very common to achieve a yield lower than 100%. But when it's less than 100% from 0% to 50%, it results in a huge loss in the product, and it's a complete waste of reactants. And then when it's greater than 100%, it's normally caused by the product containing impurities that add weight to the final product, and you can see here that the mass is greater than the mass of the entirely pure product. So here are some examples of theoretical yield in everyday use or real life experiences. Uh, for example, pharmaceutical production. They constantly deal with theoretical yield with having to go through several reactions and using very costly chemicals. They want to produce the most yield out of all their products as possible to save cost. And then in baking, when you're dealing with contents like flour, baking soda, eggs, you want to make sure that your yield in the end is the most that you can produce. And then in metal extraction from ores, so when people are trying to extract the metal from ores, like for example gold, in gold you don't want to lose any uh, metal from the ore, so you're going to try to produce the best theoretical yield possible. So now we're facing our first problem. We're calculating theoretical yield in a question that I created. You're creating a new antiperspirant deodorant for a body care company you're working for. To create the deodorant, you need aluminum chloride, which is the active ingredient that allows the antiperspirant factor to work. As a sample product, you're only given 2.80 grams of aluminum and 4.15 grams of chlorine. What is the theoretical yield of aluminum chloride and the limiting reagent in this reaction? Straight off, you can see that we are given two masses of the reactants, and that is going to be something we're going to keep in mind here. So first thing we have to do is create a balanced equation. Um, this is crucial in solving for theoretical yield, And I've already put here aluminum plus chloride, and then giving our product aluminum chloride. Uh, this is unbalanced, so now we have to balance it. So after going through, we should have 2, 3, and 2 for a balanced equation. And I've put under here a table to show the balancing process that I've gone through. And we would have 2 aluminum here in front, and 3 in front of chloride, and then 2 in front of the aluminum chloride to give us a balanced equation. And then we have our next step, which is converting the reactant masses to moles. So first off, the first step we do is we take our given mass that we had from earlier, 2.80 grams of aluminum, and then we would divide it by the molar mass of aluminum, which I've also shown in the picture below. And then that would give us 1.04 times 10 to the power of negative 1 mole aluminum. And then below, we would have our chlorine mass, which is 4.15 grams, divided by the molar mass of chloride. And since it's a diatomic, we have to times the molar mass by 2 so that we can get the both chlorines in the equation. And that would give us 5.85 times 10 to the power of negative 2 mole chloride. And you can see here that our equation is right because we have canceled out the grams in both of the uh, reactants to leave us with just mole. So now we're moving on to step 3, which is determining the limiting reactant. And I provided the balanced equation, as you can see there, because what we're going to be doing is we're going to be timesing the moles of both reactants by the mole ratio to see which reactant gives us the most product, which is aluminum chloride. So first we start off with aluminum. We take the moles 1.04 times 10 to the power of negative 1 mole aluminum times the mole ratio. As you can see in the balance equation, it is 2 divided by 2. And then you equal that, and then you are left with 1.04 times 10 to the power of negative 1 mole aluminum chloride, which is the same amount as the aluminum. And then we move down to chloride, which is 5.85 times 10 to the power of negative 2 mole chloride, times the mole ratio. As you can see here, it's 2 divided by 3, and then you equal that, and it leaves you with 3.90 times 10 to the power of negative 2 mole aluminum chloride. So chloride has produced the least amount out of the 2 reactants, so therefore chloride is the limiting reagent. So our final step here, step 4, is to calculate the theoretical yield. What we have here is the same equation as what we had in step 3, which was for finding the limiting reagent, which we now have is chloride, and we are left with 3.90 times 10 to the power negative 2 mole aluminum chloride, because that will be our final product. Uh, Converting the moles to mass for the final answer is very necessary. So we do that by taking the mole of our product, 3.90 times 10 to the power negative 2 mole aluminum chloride, and timesing it by the complete molar mass of aluminum chloride, which I've shown the process of below, which is taking 26.982 grams aluminum, which is the molar mass, and then adding it to 3 times 35.5 grams chloride because we have 3 chlorine. And that will give us 5.20 grams aluminum chloride. So 5.2 grams is going to be our final answer for calculating theoretical yield. Thank you for watching my presentation.